slide. Let me get back here so you can see it. And now I am in Chapter 2, Section 2. So you can do the reading in our book on Wiley Plus, Chapter 2, Section 2, which is entitled Instantaneous Velocity and Speed. Okay? All right. Let me get this mode so that you can see it a little bit better. Instantaneous velocity and speed. So here's our motivation for defining yet another quantity to study kinematics. Average velocity is a kind of rate of change of position, but it's over a finite time interval, like the 5-second interval we just saw for the bead on the wire. There might be times when we're interested in rate of change of position, how fast and in what direction as a particle moves, but at a particular instant in time. Not over a drawn-out time interval, but at an instant. So let's introduce a new quantity, instantaneous velocity, which, by the way, most physicists just call velocity for short. Okay? But for now, I'm going to use the full terminology, instantaneous velocity. What is its definition? First, in words. In words, instantaneous velocity is defined to be average velocity in the limit as the time interval delta t approaches 0. But we mean that word limit in a very precise mathematical way, as you will be learning in your calculus class, and I'll get to in a moment. But instantaneous velocity is average velocity in the limit as the time interval delta t approaches 0. First, the SI unit of instantaneous velocity. Well, it's meter per second, because it's the unit of average velocity, which is meter per second. Now, what's the symbol or the notation that we use for average velocity? Just plain old lowercase v, script or italic v, okay, when you represent a mathematical symbol in physics. Here's its definition. 3 bars means defined. It's what a mathematician calls a limit as the time interval delta t goes to 0 of average velocity. And there's the mathematical expression delta x over delta t for average velocity. Now let me just elaborate. This is just elaborating that. It's the limit as delta t goes to 0. And in the numerator, I've now expressed what I mean by delta x, displacement. I mean change in position. The initial position is x at time, which is the position at time t. And the final position, x, is at the later time t plus delta t. And that's what this notation means in the numerator. And you divide by delta t. And you take the limit as delta t goes to 0. Now, if you're astute with your algebra, you should be a little bit concerned by this definition, because it looks like, doesn't it, that our prescription is to take this fraction, x at time t plus delta t minus x at time t, divided by the quantity delta t, and take the limit as delta t goes to 0. But the delta t is in the denominator. So it looks like I'm taking a fraction and I'm making the denominator go to 0. And my math teachers taught me that a fraction with a 0 in the denominator is undefined. So haven't we just set ourselves up for a problem here? Sure does seem so. But here's where the whole idea of this limiting process is very clever. It turns out that the numerator, x at t plus delta t minus x at t, is also going to 0. So what I actually have is a fraction with a 0 divided by a 0. And if that limit is done in a very careful way, the output, the answer, what comes out of that limit, can be finite and have meaning. And it does. And that's what your calculus professor will be spending a very long time in Math 110 teaching you about. How to do that limit and how it can be done properly, such as that you end up with an answer at the end that makes sense. Now you need to get used to the notation here, because that whole limiting process of delta x over delta t as delta t goes to 0, that's very tedious to write all that out. So we use shorthand notation, and there it is, dx over dt. That's the notation you'll see. So that is another way to express instantaneous velocity. Now, to use the words, we say instantaneous velocity is the derivative of the position with respect to time. That's what this notation dx over dt means. The derivative of the quantity labeled x is the position on the x-axis, with respect to the quantity labeled t, time. Dx over dt means the derivative of position with respect to time. But we also use the words rate of change of position. A derivative measures the rate of change of a function. Okay? And instantaneous velocity is the rate of change of position. So with instantaneous velocity in kinematics, we are watching a particle and we are measuring the rate of change of its position at any given time. Now, I understand that the whole concept of a derivative is from calculus, and that may be new to you. You may have had calculus in high school. You may have only gotten up to pre-calculus. If you've not seen the whole concept of a derivative before, it can be a little bit daunting. And in a later video lecture, I'm going to be emphasizing those things that you need to understand right now about a derivative in order for us to continue in Chapter 2. Okay? So I'll have more to say about derivatives in an upcoming video lecture, but in Math 110, you're going to be spending weeks learning about derivatives. Okay. For now, let's continue. First, let's next emphasize that instantaneous velocity, like average velocity, is a vector quantity with both a magnitude and a direction. And here comes another bit of terminology that you just have to be aware of. When we talk about the magnitude of instantaneous velocity, just the magnitude part, we have a separate word for that, instantaneous speed, and we got to use all these words correctly. Instantaneous velocity is the rate of change of position. It's a vector. When you talk about only the magnitude part, we call it the instantaneous speed, and it's just a measure of how fast a particle is moving without worrying about what direction it's moving in. And if you want to be really careful, a good way to denote the magnitude of instantaneous velocity, i.e. instantaneous speed, is to write the v symbol with absolute value over it. That way you're telling your reader, I just mean the magnitude part, the instantaneous speed, how fast. But I'm not telling you direction. The direction, of course, is the direction in which the particle is moving at a given instant. And that could be to the right on an x-axis, i.e. plus x direction, or it could be to the left, negative x. We're going to be doing practicing with these ideas, don't worry. Let's start with a little bit of graphical interpretation of instantaneous velocity. So let me go back to Wiley+, and now let me open up another animation that you can find on the Wiley+ site, average velocity in the limit of decreasing time interval. And this shows a lot of information, in fact. And it's our first example of what's called a position time plot. It's a bit of an abstraction. Here's what we've done. Remember that bead on the wire that I showed you earlier in this lecture? Where we actually showed you a bead moving along a horizontal x-axis. That was the physical motion that we were actually literally watching. We are now representing that more abstractly by a graph with a vertical axis and a horizontal axis. The horizontal axis is time measured in seconds. You can see it down there, 0, 1, 2, 3, 4. The vertical axis is the x-coordinate or x position of the bead in meters. It happens to start at 1.5 and go up by 0.5 meter increments to 2, 2.5, etc. And the blue curve that you see is the plot of position of the bead as a function of time. Okay? And we need to be able to look at this kind of abstract position time graph and visualize the motion. And if you look at that blue curve, it tells you that when time was 0, x was 2 meters. If you remember that video I showed you of the bead, that is where it was. It was at x equals 2 meters when t equals 0 seconds. And as the time goes on, the x gets larger. You can see then, follow the blue curve, that the x-coordinate rises to about 4.25 meters maximum. And then as time goes on, the x-coordinate starts to go back, right? And go back and goes through the origin and keeps on going to the left. That's what this curve is telling you. Okay? Okay, now there's other information on this graph besides just the blue curve with position versus time. It also demonstrates a graphical representation of average velocity for a time interval. Now, right now, the time interval is set at delta t equals 2.5 seconds. The time interval starts at t equals 0 and ends at t equals 2.5. And the delta t is represented by the green rectangle down along the time axis. That's the time interval, delta t. Now, for that time interval, there's a delta x. There's a displacement, a change in position. The initial x is 2 meters, and at the end of this time interval, it looks like the final x is about 3.25 meters. And so the delta x is represented by the red rectangle on the x-axis. See it over there on the left? And then I also have a black straight line that connects two dots on the blue curve. At x final, t final, there's a black dot, and then at x initial, t initial, there isn't an actual black dot, but you can imagine one there. And then we've just drawn a straight line in black that connects x, the final point and the initial point. And the slope of that black straight line in the video, that's V average, because the slope is rise over run. The rise is delta x, the red rectangle. The run is delta t, the green rectangle. Delta x over delta t is, for this graph, rise over run, that's slope. So the slope of that straight line is the average velocity for the time interval delta t. And if you do that calculation here, you'll take 3.25 minus 2 is 1.25 meters for the delta x, divided by 2 seconds for the delta t, and you get 0.5 meters per second. And the animation actually displays that. Now, with this slider, I can change delta t. Okay. Let's reduce the delta t, see how close we can get, to 2 seconds. Now the straight line connects the initial point and the point on the curve when t equals 2 seconds, which corresponds to x equals 4 meters. Now you take the slope of that black line to get the average velocity for that time interval, and you discover it's 1 meter per second. I can make the time interval smaller and smaller. There we are at delta t equals 1 second. And the slope of the black line is now 2 meters per second. And that's the average velocity for the time interval that starts at t equals 0 and ends at t equals 1 second. And I'm now going to take the limit as the delta t gets smaller and smaller, with the t initial always being equal to t equals 0. That is graphically the same thing as in calculus taking the limit as delta t goes to 0. Now this slider doesn't let me have delta t go all the way to 0. The smallest I can get is delta t is 0.05 seconds, but it's showing you that I'm approaching a black line here that just glancingly touches the curve. And such a line that glancingly touches the curve at one point is called a tangent line for the curve. So what we see is happening is that as delta t goes to 0, I'm getting a straight line that's tangent to the curve at time 0, and the slope of that line is the average velocity, and the limit as delta t goes to 0, but that's what instantaneous velocity is. Okay? So we're getting to a nice geometrical interpretation of instantaneous velocity. If you have a plot of position versus time, x versus t, the slope of the tangent line to the curve at any given time is the instantaneous velocity of our particle at that time. So what we want to be able to do is take a plot of position versus time, like you see here, and kind of tell the story of how the particle is moving. So now let me show you the same curve. It's really the same position versus time curve. But now the little slider that I have is labeled T1. And as I move that slider, it draws the tangent line in black to the position time curve and gives me the slope of that tangent line, and that's the instantaneous velocity v. So for example, in this position versus time curve, I have the t1 slider set to 0, so the tangent line is at time 0, and you can see the black line there, and you can see it has a positive slope. And it turns out the slope of that line is exactly 3 meters per second. So the instantaneous velocity of the particle at time 0 is 3 meters per second. That means the particle is moving at a rate of 3 meters per second in the positive x direction at time 0. So again, you need to be able to tell me the story of the particle's motion. Let's change the time slider to t1. And the tangent line adjusts to always stay tangent to the curve. We're coming up on time 1 second. That's pretty close. There we are. So now we're at the time of 1 second. There's the tangent line, the black line. The animation tells me that v is 1 meter per second, so that's the slope of that curve, 1 meter per second. That tells me that it's moving at a rate of 1 meter per second, so not as fast, but still moving in the plus x direction. Okay? Can you see from this graph when the particle is at rest? For just 1 instant, there it is at rest. You see how you find out what it would be? It would be the time when the tangent line is perfectly horizontal. It may be hard to get it exactly. Oh, there we got it. It looks like the time is 1.5 seconds. Then the black line, the tangent line, is perfectly horizontal, which means it has a slope equal to 0, which means the instantaneous velocity of the particle at this 1 instant is 0. It is at rest for this 1 instant. Now let's have the time progress. Now we're going up to 2 seconds. Now notice the tangent line has a negative slope. And in fact, the animation tells me v equals negative 1 meter per second. That means it's moving at instantaneous speed of 1 meter per second, but in the negative x direction. Now moving to the left. Suppose I move up to a time of about 3 seconds. Now it's very steep and negative slope. And I see the velocity is negative 3 meters per second. Okay? There's a lot of information in a velocity time plot, and we need to be able to interpret it. Okay? Here's another question. Which way is this particle, remember it was a bead on a wire, which way is it moving when it passes through the origin? We need to be able to answer that from this graph. Well, you've got to find the velocity when x equals 0. Let's see if we can get it. There we are, that's pretty close, right? The x is 0 here, because the x is the vertical axis. But the velocity tells me, well, what the rate of change of position is. So I have a pretty large negative slope to my tangent line. In fact, the v is negative 4.12 meters per second. Negative sign tells me that it's moving in the negative x direction. Okay, this is our first introduction to a number of kinematic quantities. I'm going to leave you today by going back to my slide, and I want to refer now to the position time graph that you see in front of you. Okay, right here. Position x and time t in seconds. And you can see a curve there that is telling us the story of some particle that was moving along an x-axis and was observed with time. I'm going to now ask you a series of simple little short answer questions, and I'm going to want you to record your answers, write them down on a piece of paper, and you can pause this video and replay my questions as much as you want, but write down your answers. And then I want you to go to our Blackboard site, and I will have a discussion forum for this video lecture, 2.1. And I want you to go into that discussion board and type your answers to these questions. And this will be considered class engagement. Okay? All right, so we're using this graph of position time that you see encircled here. Here's the first question. When, at what time value or values, is this particle at rest? You can only answer based on the curve that you see here. At what time or times is this particle at rest? That's question 1. Question 2. In what direction is the particle traveling at the time t equals 0? In what direction is the particle traveling at time t equals 0? Question 3. How many distinct times does the particle pass through the origin? How many distinct times does the particle pass through the origin? And question 4. In what direction is the particle traveling at t equals 3 seconds? In what direction is the particle traveling at t equals 3 seconds? So, answer those questions in the discussion board that I will post on Blackboard. Okay, that is all for our first lecture.